Given the function f of x equals x cubed minus 6x squared plus 9x, find all intercepts, critical numbers, intervals where the function is increasing and decreasing, local maximum and minimum values, inflection points, and intervals where the function is concave upward and concave downward, then use that information to sketch a graph of the function. All right, so we've got all sorts of things going on, but we also now are being asked to find the intercepts. So we can start with that. The y-intercept is going to be 0 because there's no constant term. It's pretty easy. So the y-intercept is at 0, 0. We also want the x-intercepts. And to do that, we need to set the function equal to 0. So that's going to be x cubed minus 6x squared plus 9x, which equals 0. We can factor out an x, giving us x squared minus 6x plus 9 equals 0. And this is the same as x minus 3 times x minus 3. So we can see, in addition to 0 being an x-intercept, which we already knew because it was also the y-intercept, we also have an x-intercept equal to 3. So we're going to have 0, 0, and 3, 0 as our x-intercepts. All right, so we've got our intercepts down. Now we need to find the critical numbers and then where it's increasing, decreasing, etc. To do that, we're going to need the derivative of our function. So that's going to be 3x squared minus 12x plus 9. And we can factor out a 3 from that, giving us x squared minus 4x plus 3. And we can factor that as well into x minus 3 times x minus 1. So the critical numbers are going to be 3 and 1. X equals 3 and x equals 1. We can make our sign chart here for that. So we've got 1 and 3. And then the factors there are going to be 3, x minus 1, and x minus 3. 3 is always positive. X minus 1 is going to be positive to the right of 1. And x minus 3 is going to be positive to the right of 3. So our derivative is going to be positive, negative, positive. It's going to be increasing, decreasing, and increasing. So we're going to have a max at 1 and a min at 3. Now, we're going to want to know the function values there so we can know where the maximum and minimums occur. But the interesting thing here is the minimum happens at 3, but we know that when x is 3, y is 0, because that's one of the x-intercepts. So we're going to have a minimum at the point 3, 0. And then our maximum when x equals 1, we can plug in 1 to that function, and we end up with 4. So it's going to be 1, 4. So that gives us a minimum value and a maximum value. And we know when it's increasing and decreasing. We just need the concavity at this point. So to get that, we're going to want the second derivative. And for that, we can just differentiate the first derivative. That's going to give us 6x minus 12. Okay, and that is never going to be undefined, so we're not going to have any critical numbers from that being undefined. But it will equal 0, specifically when x is 2. Pretty easy to solve that. So we can make a sign chart if we want for that. It's a pretty lonely sign chart, but that is still fine. Our factor is 6x minus 12, which is going to be negative when x is less than 2 and positive when it's greater than. So we're going to be concave downward and then concave upward. And we'll have a point of inflection at 2. And if we plug in 2 to that function, we're going to get 2 as our function value. You can use a calculator, you can write it out, you can try it in your head, Just want to save us some time. Our point of inflection is at 2, 2. And I think that is all the information we needed to sketch it. All right. We have our y-intercept at 0, 0. That's also an x-intercept. The other x-intercept is at 3, 0. We had a local minimum at 3, 0, a local maximum at 1, 4, a point of inflection at 2, 2. If we look at our intervals, we know that the function is increasing to the left of 1. So increasing on each of those. And then it's decreasing from 1 to 3, and then increasing again. And then the concavity is downward until 2, and then upward. So if we want to draw this, we know that we've got a local maximum here and a local minimum, and we're decreasing between those, but we're concave down and then concave up. So it's going to look something like this. And I knew that this was a local maximum and this is a local minimum, and that derivatives were 0 there. That's why I made those flatten out there. On the right-hand side, after 3, we are increasing and we are concave up. So it's going to look something like that. On the left-hand side here, the function is increasing and concave down. So it's going to look something like that. But it also has to go through the origin. So it's going to be something like that. I missed the origin a little bit. Not perfect. But that is what we have. Actually, can I undo that? Yeah, let's go back in time magically. I think it's nice to fix that instead of leaving it like that. And there we are. That is our graph. We've got accurately portrayed local maximum and minimum, point of inflection, intervals of increasing and decreasing, and concavity. The intercepts are all accurate. That is a pretty good graph. If we were to have just made a table of values, we might have gotten these same points, but we wouldn't have known if this was a maximum or if this was a minimum. There's no real way to tell without using derivatives. And there you have it.